Hello, this video we're going to do some runtime analysis on linked lists. I'm going to assume that you have watched other videos regarding linked lists in which we discuss how to insert nodes in different positions, how to delete nodes in different positions, how to traverse the list, and how to count the numbers of nodes. Two things that you should be aware. The runtime analysis that we are going to do today is based on our own implementation of a linked list. In other words, we're not using the linked list class in Java that was discussed in a different video. This is our own implementation. The second thing is that there are many different ways in which a person could implement a linked list, right? So if we're not giving enough set of instructions and other specifications, we could think about a linear linked list, which looks like the one below, and every node has a reference called next, and that's the standard linear single linked list. But we could also have a double linked list, and that means that every node now has two references, one which refers to the node that follows, and one which is called previous that will refer to the node before. So we have now two references, one for the node before, one for the node after. That's going to affect our analysis. Also, most of the time, we have a linear linked list just with a front reference. In other words, looking at this picture, this is the typical linked list in which we have only one external reference called front or head, and that refers to the very first node. But in some cases, you're going to see that it's possible to implement a linked list that have two references, one that refers to the very first node and one to refer at the very last node. And if we do that, that's going to affect the runtime analysis. And finally, we could have lists, either single or double, where the end of the list is referring to the front of the list. In other words, this reference doesn't have value node. The reference of the last node refer back to the first node, and then it creates a circular linked list. The lesson to learn here is that when you do a runtime analysis of the linked list, you need to know the implementation of the linked list. Is it linear? Is it circular? Is it single? Is it double? Do you have a reference to the back? So on and so forth. In this video, we're going to assume that we are analyzing the most basic linked list, which is the one that has only a reference to the first node that we call front, and where every node has a single reference called next that refers to the node that follows a particular one. So having said that, to insert nodes on a linked list, we're going to consider the three cases that we already studied. For example, inserting a node at the front of the linked list, that's going to be O1. Why is that? Because we know where the first node is, so the size of the list doesn't affect the performance of this. So it's constant, it's independent of the numbers of nodes that we have on the list. On the other hand, if we're going to try to insert a node at the end in this linked list, we don't know where the end is. So we need to traverse the list, as we discussed in that video, until we find the last node, and then we do the insertion. So traversing the list is obviously directly proportional to the numbers of nodes on the list. So we said that inserting a node at the back of the list is ON, directly proportional to the numbers of nodes that we have on the list. Finally, we discussed inserting a node somewhere in between, not at the very beginning, not at the very end, but somewhere in the middle of the linked list. And again, think about a list that have 10,000 nodes, so there are many places that consider interior nodes. And again, we don't have indexes like in an array, so we don't have direct access, so we need to find the place of insertion. Think about maintaining a list in alphabetical order or in increasing order. So every time that you insert a node, you need to insert the node in the right place. Well, before we insert, we need to find what the right place is. And that's going to require traversing the list. And because of that, we said that inserting an interior node is directly proportional to the size of the list, to the numbers of elements in my collection. Let's talk about now deleting nodes. So to delete nodes, again, we have the three cases. The best scenario is deleting the front because we know where the front of the list is, so that is constant, that is independent of the numbers of elements. Deleting the last one, again, is the same discussion that we have for inserting nodes. As a matter of fact, the same reasoning can be applied to these two. Deleting any node that is in the middle or somewhere in the middle of the linked list, we need to find the node. even because we're given a value or because we're given a position. So we sort of like need to search, and in order to do that, we need to traverse the list. And to find the end of the list, if we don't know where the end of the list is, like in this case, then we need to find the end, and that requires traversing the list. So deleting the last node is going to be directly proportional to the size of the data. This will give you some motivation, by the way, in the case of deleting the last node and inserting the last node, to have a reference that let us know where the end of the list is. Let's talk about the state of the list. So a question that is always asked is the list empty? Is the collection empty? Okay, so for that we built a Boolean method, and to determine whether or not it's empty is independent of the size of the data, because we have a reference called front that let us know where the first node is. So what we do is to check the value of null of front. If front is null, then we know that the list is empty. So finding whether or not the list is empty is independent of the size of the data. What about other operations? Well, we have the following, which we implemented at different times. So searching. The best scenario is O1. And why is that? Well, because, again, the value that we're looking for is at the front of the list. We know where the front of the list is. On the other hand, the worst scenario will be that the value that we're searching for is toward the end of the list, which means we're going to end up traversing all the list, all the values, or most of them. Now, what is important to realize is that the average scenario, as we know, is that we don't find the value at the very beginning of the collection or at the very end, is somewhere in between. So we talk about an expected running time, which happens to be ON. So the expected running time of a search of a linked list, as we have implemented, is directly proportional to the size of the data. Determining the size of the linked list, obviously we have to count all the nodes, every single one. And to do that, we have to traverse the entire list, and obviously this is directly proportional to the size of the collection. And finally, if we do something like similar to what we had discussed in the past, like the method get, which is an accessor, just retrieve a value in the collection, or the method set, which is a mutator to changes a value in the collection, we need to find it, right? And again, we don't have indexes. So we need to traverse the list, comparing one value at a time in every node until we find the node that we want to display or the node that we want to modify. So the worst scenario will be, again, we have to traverse the entire list or almost the entire list. The best scenario is independent of the size of the data, because we know again where the first node is. But the expected running time, the average running time of this operation will be ON. So you see how searching for a node operation has the same values in terms of performance as get and set, because the get and set are a search in disguise. It will be a good exercise for you to do the same analysis that we have done here, but considering, for example, what happened if you were to have a linear list with two references, one to the front and one to the back, and then do a third analysis where you have a linear double linked list where you have two references, the next and the previous reference in every node, and see how having these two references or having these two references is going to affect the performance of the operations that we just discussed.